Good morning. I'm Mark Goldsmith. I'm the CEO of Revolution Medicines, and with me today are Peg Horn, our Chief Operating Officer, and Steve Kelsey, our President of R&D. Our mission at Revolution Medicines is to translate frontier oncology targets to outsmart cancer, and we're very excited to have the chance to tell you our story today. We'll describe for you a number of features of the company through this talk. First, that we are a clinical stage precision oncology company with a deep R&D focus on RAS-dependent cancers. Second, that we have a cohesive and complementary product pipeline to maximize benefit for cancer patients, primarily through synergistic combinations. Third, that our product pipeline was produced by a highly productive innovation engine, strong company capabilities, and broad company leadership. We have a strong financial position, top-tier investors, and finally, we'll illustrate for you examples of our synergistic value-enhancing business transactions. First, our innovation engine. We have a highly productive platform and capability focused entirely on genetic drivers of RAS-dependent cancers, and there are three pillars to this product engine. The first is a deep chemical biology and cancer pharmacology know-how directed explicitly to define critical vulnerabilities of frontier RAS and the related mTOR pathway targets and their signaling circuits in order to understand the resistance mechanisms that we need to overcome. The second is a sophisticated structure-based drug discovery capability that extends to proven access to complex chemical space, meaning compounds including those that are beyond traditional rule of five, tailored specifically to these elusive cancer targets. And then finally, a deep focus on precision medicine, precision oncology, in which we're matching patients with genetic definition, those patients that carry tumors addicted to the RAS and mTOR pathways, and defining appropriate compounds for their use. Now let's begin to talk about our pipeline, which will be the bulk of this presentation. We have a rich pipeline based on our understanding of both the biology and the genetics of RAS-dependent cancers. We've created this pipeline specifically in order to be able to strategically combine multiple drugs in order to overcome the resistance loops that feed oncogene addiction. Shown in this slide are two canonical and rather disruptive pathways from receptor tyrosine kinase growth factor receptors that normally drive the control of normal cell growth. However, when these pathways are exaggerated and excessive signaling is driven through cancer oncogenes, we then see excessive growth, excessive cell survival, and the expression of oncogenes that can transform the cells. We've identified selected nodes throughout these cascades and have layered them onto the cascades shown here as our drug discovery targets. The top of the pathway is defined by SHP2, which is an important convergent signaling node receiving receptor signals from virtually all receptor tyrosine kinases. That's a master regulator of the pathway. And then as we work down the RAS pathway, we see SOS1, an important but differentiated regulatory node. We see multiple mutations of RAS that can drive cancer downstream of those signaling nodes. And then mTORC1 on the right side, which is an intersecting target and pathway that is also crucial for abrogating this sort of oncogenic activity. So we'll talk today about SHP2, and we'll talk about our multiple RAS targets. We won't have time to talk about SOS1 or the 4-ABP1 mTORC1 program. So let's begin with SHP2. We'll spend about half of this presentation on SHP2, and we'll tell you the underlying biology as well as the clinical status of this program, and then we'll turn to the RAS targets. As I mentioned, SHP2 sits at the top of the signaling cascade. It's a convergent signaling node that receives signals from multiple receptor tyrosine kinases and funnels those signals into activation of RAS and its downstream effector functions. RMC-4630 is a highly potent, selective, and orally bioavailable compound that inhibits SHP2, and it's been well recognized that inhibition of SHP2 would abrogate signals that are coming in from receptor tyrosine kinase mutations or activation events that are upstream of SHP2. What's less well appreciated is that inhibition of SHP2 can also attenuate signals driven by oncogenic drivers that are downstream of SHP2. And we'll show you that in the next slide, and this has become a foundational feature of our clinical development program that is identifying patients with mutations downstream of SHP2 that could be sensitive to SHP2 inhibition. So this is our first data slide. It's a set of preclinical studies performed with human cancers that carry specific mutations in the RAS signaling pathway that have been engrafted into mice and then studied in the absence or presence of RMC-4630, our potent inhibitor. In the upper left is a first example of this. It is a representative of EGF receptor-driven tumors, and as I mentioned, one would expect that inhibition of SHP2 would abrogate those EGF receptor-driven tumors, and that's in fact the case. Shown in the black line, and you'll see this throughout the presentation, is the control animals that receive no treatment, and in that case, the tumors completely overtake the animals and resulting in their termination. In the presence of RMC-4630, shown in the green line, treated at 30 milligrams per kilogram per day, we see dramatic attenuation of tumor growth in this context. Now that's the expected result. The less expected result introduced by Revolution Medicines are the next three panels, which show you examples of common, potent activating mutations in targets that are downstream of SHP2 and yet remain sensitive to inhibition of SHP2 upstream of them. In the upper right is a very famous example, the KRAS G12C mutation. Here is a lung cancer engrafted into animals that shows aggressive growth in the absence of treatment and then shows dramatic attenuation with RMC-4630. Similar results are seen with the BRAF class 3 mutation shown on the bottom left and with the NF1 loss of function mutation in the bottom right. So all of these serve to substantiate the claims that we made several years ago, and as you'll see when we get to the clinical section, serve as a genetic foundation for our clinical development strategy. Now I'd like to spend a moment digging a little bit more deeply into the pharmacology of RMC-4630 because we've discovered an alternate dosing regimen that can maximize both the tolerability of the drug as well as its efficacy in preclinical models, which we believe translates into humans. Shown on the left is an expansion of the experiment shown in the previous slide with a KRAS G12C driven tumor, and in this case, instead of aggregating all 10 animals into a single green line, we're showing you the individual results with each animal in the group of 10. And in this case, treatment with 30 milligrams per kilogram per day, that is the maximal tolerated dose, results in some animals showing deep regressions of their tumors. You can see the curves falling well below the starting point. Some animals showing tumor stasis, that is a flat line, and a few animals showing persistent tumor growth. That's the best that we can do with daily dosing at maximal tolerated dose. However, on the right side is shown an example of an alternate dosing regimen. We describe that as an intermittent regimen defined in order to achieve discontinuous target coverage. And in this case, we're dosing every other day, but now we're able to give as high as 200 milligrams per kilogram per day. And in these animals, all of the tumors showed at least stasis, and many animals showed tumor regressions or even deep regressions. We believe the basis for this is that the intermittent dosing regimen allows us to achieve very high Cmax levels upon dosing, which is important for driving an apoptotic threshold, that is converting cells into apoptosis, resulting in their death and tumor regression, whereas a rest period provided by the intermittent dosing allows the trough levels of the drug to come down, which allows normal cells to recover. Steve will address this a little bit more when we get into the clinical presentation. But this is an important innovation and one that we think will be very important in achieving the maximum benefit for patients in the clinic. So let me just introduce the clinical program here, and then I'll turn things over to Steve to walk you through our first clinical study. We have a broad-based and parallel development program designed to maximize the potential utility of RMC-4630 in various contexts. We introduced the compound into the clinic in late 2018 after filing an IND, and we began a monotherapy program. It's a very extensive monotherapy program that tests both doses through dose escalation as well as alternate schedules in order to achieve the intermittency that I alluded to earlier. Based on the results that Steve will describe for you, we now believe that this compound is clinically active, and based on that, we're able to move swiftly into multiple combination regimens, which I'll talk to you about in just a few minutes. So let me now turn things over to Steve Kelsey.
Thank you very much, Mark. I'm going to show you about 8 slides which summarize the early clinical data to date with RMC-4630. I think there are 3 things I want you to take away from this presentation, notwithstanding the fact that the data is preliminary. The first is that RMC-4630 is clearly an active drug in the clinic, and the activity is, as we predicted from the preclinical data, greater in non-small cell lung cancer that carries a KRAS G12C mutation. The activity is not restricted to that, but it is at least greater in that patient population. And as I say, this gets to the translatability of our preclinical data into what we see in the clinic. The second is that we have found that we can achieve active concentrations of RMC-4630 without incurring intolerable toxicity. And that was not something that was inevitable at the beginning of the program. In fact, a lot of people expressed some skepticism as whether we would be able to achieve that. And the third is that the activity and the tolerability, which is in part enabled by this intermittent dosing strategy, which we feel is part of our innovation, does set up the program for the combination strategy which is currently underway. The phase 1 study design is fairly conventional in as much as it is a conventional 3+3 study, dose escalation study for patients with advanced solid tumors. There are 2 things about this study that I'd like to point out that are not conventional. One is that the dose escalation, as you can see from the boxes on the left, converts from daily dosing to intermittent dosing. And in this instance, the intermittent dosing is on day 1 and day 4 on a weekly schedule. So the patients only take RMC-4630 on day 1 and day 4 of each week. When I show you the PK, it will become clear why that is. The second is that we did allow each dose level to be expanded below the maximally tolerated dose, which is a little unconventional, but at least it increases our patient dosing experience and gives us a lot more information on which to base the conclusions that we've been able to draw on so far from the preliminary data. The patient baseline characteristics are fairly standard for a solid tumor phase 1 study. The number of prior cancer therapies for each patient is 4 with up to 11. So these patients are, as is conventional, heavily pre-treated. The patient base is very much biased in favor of lung cancer and colon cancer, and this reflects the incidence of what we call putative SHP2 sensitive mutations in the RAS signaling pathway in those diseases, and was entirely deliberate when we focused the investigator base for this study at the beginning of the trial. The early clinical data, the safety data, suggests that we have a drug that is reasonably well tolerated. The toxicities that we see, but the nature of the toxicities or adverse events that we are seeing is entirely consistent with the mechanism of SHP2 inhibition. And the toxicities that you see on the slide reflect the toxicities to tissues that are both dependent directly on SHP2 and those that are dependent on RAS signaling, which has already been described for the class of drugs that inhibit this pathway, in particular the EGFR inhibitors and the MEK kinase inhibitors. The early data that we have, and bear in mind we only have 14 patients that have so far received the intermittent schedule, does suggest that the intermittent dosing schedule is better tolerated than the daily dosing schedule. And because of this, all further studies, including the combination studies, are going to go forwards using this intermittent dosing schedule. This is the pharmacokinetics of RMC-4630. Over the first dosing period. And as you can see, pretty much every dose level achieves a trough plasma concentration which is above the EC50 for phospho-ERK inhibition in tumors. The lower dose level, the 20 milligram daily dose level, does not achieve that on day one, but by the time the patients have achieved steady state, the trough concentration is above that EC50 line. So the tumors are being at least partially inhibited for the entire dosing schedule. More importantly, though, the two lines at the top, the red line and the blue line, which reflect the PK from the intermittent dosing schedules, you can see that the Cmax levels now are achieving this EC75 level, which is approximately at this apoptotic threshold that Mark talked to you about. The concentration of RMC-4630, which is required to trigger apoptosis in tumors and which is then consistent with tumor shrinkage in patients. As the patients spend at least 3 days off drug before they take another dose, you can see the plasma concentration drifting down towards this EC50 level, which allows normal tissues to recover, and we think this is important for the ultimate tolerability of the drug using this schedule. So there are a number of slides on drug activity, which of course is what people are really interested in. The first is the question as to whether the drug hits the target. It clearly does. If you look at the pictures on the right, the brown staining is phospho-ERK, almost the lowest point in the RAS signaling pathway that we can detect, we can actually measure. And you can see that at baseline, these two tumors that we took from patients who were on the study had very high phospho-ERK levels, which indicates high levels of RAS signaling pathway activation. And on RMC-4630, it is almost completely attenuated. And that happened in 3 out of 4 of the patients in whom we had repeat biopsies. The fourth patient, which Peg likes to call our sort of internal control, did not have an inhibition of RAS signaling pathway, and that turns out that they had spent 8 days off drug before they had the repeat biopsy. So this patient had no circulating levels of RMC-4630 in their blood at the time the biopsy was taken, and shows that it sort of corroborates, if you like, that the inhibition that we saw in the other 3 patients was due to circulating levels of the drug. It's also important to point out that the 2 pictures that you see were taken from patients who were receiving 20 milligrams and 40 milligrams of the drug every day, which is way below the maximally tolerated dose that we've achieved so far. This is a waterfall plot of tumor size or best response, if you like, in patients who have non-small cell lung cancer treated with 4630. The reason we have put together the data for non-small cell lung cancer is because, as you saw earlier, it's the single biggest histotype population, accounting for approximately half of the patients treated with the drug so far. There are patients with tumor shrinkage that you can see on the right. One of these patients achieved a confirmed partial response. Another patient achieved an unconfirmed partial response, which you can see is labeled as stable disease according to RECIST. 3 of the 5 patients with significant tumor shrinkage have a KRAS G12C mutation, and the one patient with a KRAS G12D mutation that had the unconfirmed partial response also had another mutation in the RAS signaling pathway, which is actually a SHP2 mutation, showing that this tumor was heavily addicted to RAS signaling. The other thing about the best response for patients with non-small cell lung cancer, approximately 2/3 of the patients with non-small cell lung cancer achieved a best response of stable disease, which gives you a disease control rate of around 67%. Even though the denominator is small for the G12C mutant patients, it's 75%, or 6 out of 8. So this drug is clearly active. It's active in lung cancer with RAS mutations. It appears to be more active in the G12C mutant patients. And the last thing I want to point out from this slide is if you look at the 5 patients on the right with the tumor shrinkage, it looks as though the intermittent dosing patients are overrepresented, even though the numbers are very small at this stage. This is a swimmer plot which shows the duration of response in those patients. I would only point out at this stage 2 things. Firstly, the data is extremely immature, and we can't really draw very many conclusions from the data at this stage. The second thing is that there's a purple line at the bottom which is broken on the x-axis, which illustrates that one of our patients has been on therapy now for over a year. This patient actually has a G12V mutation, which is not a mutation which is thought to be classically SHP2 sensitive, although there were a couple of cell lines in our panel that did show sensitivity to SHP2 inhibition, and the actual underlying biological or genetic reasons for this at this stage are unclear. The last stage in the clinical data section is a CT scan, just to give you a sense of how these waterfall plots translate into real tumor shrinkage. There are 2 lesions shown on the baseline scans, 2 completely separate sections of the patient's abdomen that with the tumor highlighted, and both of these lesions are significant lesions. They're the size of, at least the size of a fist, and you can see the very significant reduction in tumor volume that is associated with the best response. So that what you see on the waterfall plots are the unidimensional measurements. What you see on the CT scan is a sort of a cross-sectional or bidimensional, a 2-dimensional representation. And then if you turn that into a 3-dimensional size by using sort of 4/3 pi r cubed, if you like, you can see that these 50% reductions in tumor size that you see on waterfalls, which is a RECIST, can turn into very significant tumor reductions. And I think these are associated with real clinical benefit. I'd like to finish just by saying 2 things. Firstly, paraphrasing something that we heard at the recent meeting of the AACR and ISLAC for lung cancer, which is that these data, I think, show us now that there are 3 drugs in clinical development that are active against KRAS G12C mutant lung cancer. We know there's been a lot of press about AMG 510 and Mirati's KRAS G12C inhibitor, and we now have a 3rd drug. The obvious thing to do when you have 2 drugs that attack the same disease but by completely different mechanisms is to put them together, and I think that this data sets up that trial, that combination trial with AMG 510 that you saw on slide 11 extremely well. Thank you very much.
Thanks, Steve. And that's a very nice segue then into returning to an overview of our clinical trial program. I want to make 2 important points here. The first is that our SHP2 program is partnered with Sanofi on a global and exclusive basis. And I'll describe for you in just a few minutes the favorable terms upon which we entered this important partnership. And the second is that with the clinical activity that Steve just described for you, we now feel very encouraged about entering the combination clinical trials that we have always envisioned. And those are shown at the bottom of this slide, at least the first 4 of them. The first is a combination between RMC-4630 and a MEK inhibitor. In this case, we're using Roche's Cotellic, and Roche is substantially excited about this collaboration and has provided Cotellic or cobimetinib for that clinical study, which began in late 2019. The second is a combination, as Steve just alluded to, between RMC-4630 and Amgen's KRAS G12C inhibitor known as AMG 510. That study has not yet begun, but we anticipate that it will start relatively soon. And then two other combinations that I won't have time to tell you about in any detail today. One is with an EGF receptor antagonist, osimertinib, and the second is with an anti-PD-1 antibody. Both of those studies should start in 2020. But let me take a moment to show you some experiments in support of each of the first two combination studies, which we think are extremely exciting. The first is a look at MEK combination, and here the concept is that we're clamping down the pathway by inhibiting SHP2 at the top of the pathway and MEK at the bottom of the pathway and trying to abrogate the adaptive resistance mechanisms that might occur. In this xenograft experiment, again with a KRAS G12C human lung cancer tumor and grafted into mice, we either provided no drug, as shown in the black line, you're now used to seeing these from this presentation, or we treated the animals with cobimetinib or RMC-4630, in each case at quite a low dose. These are the doses well below the MTD dosing that we described earlier. Those are shown in the blue and red lines respectively. They cause anti-tumor effects. They reduce tumor growth, but they don't really cause regressions. And when the two are combined, as shown in the purple on the left line and in the waterfall on the right, it converts many of the animals into frank tumor regression. So this is the additivity of inhibiting at the top and bottom of the pathway. This has now translated into the clinic, as I mentioned. We don't yet have any clinical data to report, but look forward to doing so. And the second example is the KRAS G12C combination. Here we're talking about combining RMC-4630 with a first-generation inhibitor of KRAS G12C. We refer to these as G12C off inhibitors, and I'll explain that nomenclature in just a few minutes. Shown are two different experiments here. The first on the left is an experiment reported by Mirati in which they tested KRAS G12C inhibitor with or without one of our SHP2 inhibitors in the xenograft model, but this model is an insensitive tumor model. That is to say, the single agent alone does not drive regressions in this particular tumor model, but by combining with a SHP2 inhibitor, it's converted into a regressive phenotype, which is a very exciting concept that people want to evaluate now in the clinic. And the second example is an experiment of our own shown on the right, in which we take a sensitive tumor, a KRAS G12C inhibitor sensitive tumor, treat it, and then add to it RMC-4630. And as you can see from the purple line, we can increase the frequency and depth of the regressions through that combination. Based on this kind of work, we expect to see the combination in the clinic relatively soon through a clinical collaboration that we've established with Amgen. I mentioned that we'd like to describe for you the favorable terms upon which we entered a partnership with Sanofi. This is a global exclusive relationship around SHP2. In this relationship, Sanofi paid Revolution Medicines a $50 million upfront fee to enter the partnership. They then pay for all development costs and virtually all research costs associated with this program. Despite those economics, we retain a 50% profit share interest in the U.S. and a significant ex-U.S. royalty. We also retain the right to co-promote the product in the U.S. Currently, we lead both the research and early development of RMC-4630. We expect in 2020 that Sanofi will begin taking a more active hand, and eventually they will be responsible for registration trials. So we've spent most of this presentation so far talking about SHP2 as an upstream regulatory node, and now I'd like to turn to our view of RAS driver mutations and show you how we are going about drugging these. There are diverse RAS mutations that are responsible for human cancers. There are three different isoforms of RAS, known as K, N, and H RAS, which tend to cluster in different tumor types. There are three different mutational hotspots, glycine 12 or G12, glycine 13, G13, and glutamine 61 or Q61. And at each of these hotspots, there are as many as 6 different amino acid substitutions. So multiplying that out 6 times 3 times 3, you can see that there are dozens of oncogenic driver mutations that collectively account for 30% of human cancers in the U.S. This is an important collection or portfolio of targets. Each patient carries typically one of these mutations, and thus each mutation represents a different patient segment with a significant unmet need. The frequency of these mutations, of course, varies. There are very common mutations and there are less common mutations. They do tend to cluster in different tumor types. For example, KRAS G12C, very famously, is the most common RAS mutation in lung cancer, shown in the column here. KRAS G12D, however, is the most common mutation, or one of the most common RAS mutations, in colorectal cancer. Our strategy is to broadly approach these mutations and try to develop specific inhibitors of each of these mutations in order to address each patient segment. We've highlighted for you the first 4 of these targets that are our priority targets for the near term, but in fact we have multiple programs underway at Revolution Medicines. In order to understand our innovative approach to RAS, it's important to understand the underlying biology. RAS normally lives in an inactive or on configuration, as shown on the far left, and that's how normal cells keep RAS signaling in check. And perhaps only 5 or 10% of the RAS is in the active form in a normal cell. However, in the presence of any one of these RAS mutations, there is a significant bias towards the active or RAS-on form, such that 80, 90, 95% of the RAS in a cell is now in the active form, and that's what drives excessive growth signaling and tumorigenesis. And therefore, to us, it seems to make the most sense to try to inhibit that active oncogenic form of RAS. But after 3 decades of research, nobody has come up with a way to do that, and the closest approximation has been the emergence of inhibitors of the KRAS off form, specifically the KRAS G12C off inhibitors that are now very famous because they've shown early and important clinical activity. So we'll describe for you, though, our approach to drugging RAS on. We've been quite successful preclinically, and we've done that by taking advantage of a solution that nature or evolution has provided us. There are many examples in nature of natural compounds that bacteria have evolved in order to bind to very difficult non-druggable surfaces, an example being mTOR. And the way they came up with to do that over 1 billion years of evolution is to precipitate the tri-complex formation between 2 different proteins with the small molecule sitting at the interface between the two, where there's essentially an effective new drug binding pocket. We get to take advantage of this idea and move from evolution to revolution, in part because we acquired a company just a little over a year ago called Warp Drive Bio, in which their vision was to synthetically design new drugs that could be provided to a cell, would enter the cell, bind to a ubiquitous protein known as a chaperone protein, and then that binary complex could present the small molecule to the target of interest and bind specifically, in our case, to the RAS-on proteins. And I'd like to show you an example of that at higher resolution. Now, for the next few slides, I'm going to focus on KRAS G12C as a demonstration piece, although it is important to emphasize that at Revolution Medicines we consider multiple RAS targets to be important therapeutic targets and the subject of our investment. So shown here is KRAS G12C in the green. This is the on or active state of KRAS G12C. Binding to it is our inhibitor, shown in gold, and connected to it as well is the ubiquitous chaperone known as cyclophilin A. So this is a high affinity complex, and once formed within a cell, the RAS protein is no longer able to signal downstream, and that's because it is literally capped. The effector face of RAS is no longer able to bind to the next component in the downstream signaling, and that is the RAF, a very famous RAF protein. So this is a completely distinct mechanism of action, a completely distinct binding mechanism, and enables us to go after these active or RAS-on forms. This translates into anticellular effects shown in the upper right, which is a reduction in cellular phospho-ERK, as Steve introduced in his presentation. This also translates into anti-proliferative effects, as shown in the bottom right. We have, over the last few months, been able to begin introducing into the public domain evidence that these compounds are active in vivo models as well. Here are 2 examples of KRAS G12C-driven human tumors and grafted into mice, and you've now seen multiple examples of these, so this is familiar to you. On the left side is a lung cancer carrying KRAS G12C, showing the dose-dependent inhibition of tumor growth in the light blue line at a low dose, and at a somewhat higher dose, conversion of virtually all of these animals into a regressive phenotype. Likewise, on the right side is an example of a different tissue type, which is pancreatic cancer, again carrying the KRAS G12C mutation, and shown here is the inhibitor having a very dramatic effect, all of the animals showing very rapid and complete regression of their tumors. So these compounds are not only active in vitro, but they translate into anti-tumor effects in vivo. We believe that the biology of inhibiting RAS-on is quite distinct from that of inhibiting RAS-off, and that there are, in fact, two advantages to our approach. One is that we can attack multiple RAS mutations, and the second is that we're inhibiting the active or oncogenic form of RAS. Two examples are shown here, one on the left in vitro and one on the right in vivo. The left shows an example of a long-term culture experiment with the KRAS G12C tumor cell line. We're treating these tumors in culture with either a MEK inhibitor or one of our KRAS G12C ON inhibitors at a low dose, and you can see that it does result in some delay in cell growth, but eventually the cells grow out in the culture. But when we combine these two at the same doses, we see dramatic suppression of growth, and in fact there are no viable cells left in these cultures, indicating that a KRAS G12C ON inhibitor is very effective at combining with a MEK inhibitor, something that has not been described for the KRAS G12C OFF inhibitors. This phenomenon translates in vivo, as shown in the experiment on the right. We're just showing you the waterfall plot for simplicity here, but again, a MEK inhibitor or the KRAS G12C ON inhibitor alone has some anti-tumor effect at these doses, but when they're combined, there's a very powerful anti-tumor effect resulting in tumor regression, as shown in the green bars. So we're very excited about the combinability of the RAS-on inhibitors with other agents. And as I mentioned, although we use KRAS G12C as our most prominent demonstration piece, we have moved already into other mutations that go well beyond KRAS G12C. Here is an example of one of our priority targets. Many people have not heard of it. It's called KRAS G13C. And people haven't heard of it because nobody had any idea how to drug it, so there was really nothing to talk about. We now have an approach that we believe can be useful. Here is an example of an inhibitor from the RevMed collection binding to KRAS G13C, a specific genotype that causes human cancer, mostly lung cancers, and it's doing so in this tri-complex context that I described for you before, and shown on the right is an example of the cellular effects on a KRAS G13C driven tumor, and we will be extending this to other mutations as time goes on, giving us quite an opportunity to have benefit for multiple patient segments. So the takeaways from our RAS-on story are that the mechanism of action of these inhibitors is quite distinct. We're inhibiting the oncogenic active form of RAS. We can inhibit RAS even in situations in which the signals through the pathway are increased, such as in adaptive resistance. That we've demonstrated additive anti-tumor effects with multiple pathway node inhibitors, both MEK and SHP2 inhibitors. And finally, that there is significant breadth to this platform. We can inhibit multiple RAS mutants spanning multiple RAS isoforms with multiple hotspots and oncogenic substitutions. So bringing this all together, we have a cohesive and complementary and rich pipeline designed to maximize patient benefit for patients carrying RAS tumors, and particularly through strategic combinations of drugs. Our SHP2 program, you've heard, is moving along very nicely in the clinic with a parallel and multidimensional program. Our RAS mutational, our mutant RAS platform is delivering a very exciting compounds. We did not have time to talk about SOS1, which is still in preclinical work, but making nice progress. And finally, our mTOR inhibitor, which has not gotten any play because of all the time we spent talking about RAS, has passed DC selection stage and is now in early preclinical development heading towards an IND. So moving from that heavy science dive into a bit of business here, looking into 2020, we anticipate a number of milestones specifically for the RMC-4630 program. We look forward to beginning treating KRAS G12C patients carrying with the combination of the Amgen AMG 510 with the RMC 4630 compound, a study that will be conducted by Amgen and seems to be moving along very nicely behind the scenes. Secondly, we look forward to beginning treating patients in combination with osimertinib, something that will happen mid-year. Third, we will begin treating patients in combination with an anti-PD-1 antibody that will also start this year. And we aim to present additional clinical data, a clinical update extending beyond the disclosure that we recently made at the AACR-ISLAC meeting and that Steve just summarized for you today. In our mutant RAS-on program, two important milestones for the year would be our identification of a first development candidate, and we're moving along very nicely toward that goal. And also we expect to indicate that we've identified lead compounds for a second target during 2020. And finally, as I mentioned, we're progressing RMC 5552, which is our SOS1, our mTORC1 4BP1 inhibitor, through clinical development, through IND-enabling development, and expect to be IND ready by the end of 2020. We're in a strong financial position with over $135 million of cash and cash equivalents as of the end of Q3 2019. And I'm really proud to be standing on the stage with my colleagues. Collectively, we have a great deal of experience bringing science, medicine, and business together through creation and leadership of companies. I've enjoyed working with this group, and we think we've been very effective at building both clinical value on behalf of patients and share value on behalf of our investors. And finally, speaking of those investors, we're supported by a terrific group of high-quality investors, most of which you all know, and we look forward to continuing this process. Thanks for your attention today.